In this video, we'll introduce the Taylor series and Maclaurin series. The basic idea is we want to be able to represent a function with a power series. Notice what we have here is simply a power series, and we're now calling it f of x. If we wanted to, like we did in previous videos, we could list out the individual terms of that series. And what we're going to do now is we're going to start taking derivatives of those. So that's what we have here. This f to the n, that is the nth derivative of f at a. So this expression, the nth derivative of f at a divided by n factorial, we're going to replace that c sub n with. And that's going to give us what we have down here, the Taylor series of f at a. The Maclaurin series is just a special case scenario. Here, we're going to let a specifically be 0. And if a is 0, we have a similar function. Looks a little bit simpler simply because a is now 0. Let's look at this example. We want to find the Taylor series for f centered at a equals 0 and find the radius of convergence. Notice that since a is 0, we're actually finding the Maclaurin series. So another way of stating this question is find the Maclaurin series for f. The first thing we want to do is find derivatives for f and look for a pattern. So off to the side, let's start with f of x. F of x is e to the x. The first derivative is then e to the x. You'll see that this is a very simple example to get us started. The second derivative is e to the x. The third derivative is also e to the x, and so on. That's going to go on forever. Step 2 is we want to plug in the a value, which in this case is just 0. So f of 0, we get e to the 0, which is simply 1. Then f prime evaluated at 0, that is again 1. Second derivative at 0 is 1. Third derivative at 0 is again 1. And again, that's going to continue forever. It's not always going to be this simple. Typically, we'll need to look for a pattern, and typically it'll somehow involve n. Step 3, we'll set up the series. And then step 4, we will find r and the interval of convergence. So we'll find the radius and the interval of convergence. So f of x is going to be the sum from n equals 0 to infinity, f to the n of 0 divided by n factorial times x minus a, which is 0, raised to the n. Our goal is to figure out what this piece is here. Again, in this example, it's pretty simple. It's not always going to be as simple as this one. So let's start by listing out some terms. When n is 0, we get 1. And then when n is 1, we get x. Again, plugging in 1 for n, we'll get the numerator, which is 1, divided by n factorial. 1 factorial is 1 times x. Plus, plugging in 2, we'll get 1 divided by 2 factorial is just 2 times x squared. And then we'll get 1 divided by 3 factorial, or 6, times x cubed, plus 1 divided by 4 factorial, times x to the 4th, and that's going to continue forever. So let's see if we can find a pattern there for that nth derivative. F of x we can write as the sum n equals 0 to infinity. N factorial is in the denominator, and now look at the numerator. What's changing? Basically, the power on x is what's changing. That we can write as x to the n. When n is 0, we get x to the 0, which is just 1. When n is 1, we get x to the first, which is x. When n is 2, we get x squared, and so on. And the denominator is the n factorial from our formula earlier. So now that we have f, let's see if we can find the radius of convergence. Remember, to do that, we use the ratio test. So we'll get a little practice with that. Limit n goes to infinity, next term divided by the current term. The next term would be x to the n plus 1 divided by n plus 1 factorial. All of that divided by the current term, x to the n divided by n factorial. Let's rewrite that. We'll copy the top fraction and multiply by the reciprocal of the bottom fraction. And now let's see what we can simplify. X to the n is going to occur in the top and the bottom. Reducing that will leave us with x in the numerator. And with the n factorials, n factorial will go away, leaving us with just n plus 1 in the denominator. Now we have the limit of 1 divided by n plus 1 times the absolute value of x. That limit is going to go to 0, so we have 0 times absolute value of x, which is just 0. And remember, that is less than 1. With the ratio test, that means for all x. So our interval is negative infinity to positive infinity, and our radius is infinity. So that tells us f of x can be represented by the sum from n equals 0 to infinity of x to the n divided by n factorial on the interval from negative infinity to positive infinity. So what does that do for us? Let's say we wanted to figure out what f of 2 is. That is e squared in this case. Well, we could use this sum to help us find that. We'd have 1 plus 2 plus 2 squared divided by 2. That's 2 factorial, or just 2, plus 2 cubed divided by 3 factorial, plus 2 to the 4th divided by 4 factorial. And if we did that forever, we would actually get e squared. So if we wanted a quicker approximation, rather than adding them all up, we could add the first 5 or 6 terms and get a rough calculation for e squared. In this example, we are again looking for a Taylor series. This time we want to be centered at a equals negative 3. We'll start by listing out some derivatives. F of x is simply 1 over x. It may be helpful to think of that as x to the negative 1. The first derivative would then be negative x to the negative 2. Second derivative would be 2x to the negative 3. Third derivative is negative 6x to the negative 4. And you could keep going if you need more. I think we'll be able to see a pattern from here. Next, we need to plug in the a value, negative 3. F evaluated at negative 3. That is simply negative 1/3. First derivative at negative 3. That will be negative 1 divided by 9, or let's write that as 3 squared. The second derivative at negative 3 is negative 2 divided by 3 cubed. Third derivative at negative 3 is then negative 6 divided by 3 to the 4th. And again, that pattern continues forever. So f of x, which is 1 divided by x, we can think of as the sum from n equals 0 to infinity of the nth derivative of f at negative 3 divided by n factorial times x minus a. X minus negative 3 is x plus 3 raised to the n. So let's list out some terms and see if we can find that pattern that we need. We have negative 1/3 times x plus 3 to the 0 divided by 0 factorial, which is really just 1. Then we get the next nth derivative was negative 1 divided by 3 squared times x plus 3 to the first, all divided by 1 factorial, which is again just 1, plus negative 2 divided by 3 cubed, x plus 3 squared, all divided by 2 factorial. Let's do one more. Negative 6 divided by 3 to the 4th times x plus 3 cubed, all divided by 3 factorial. And that pattern will continue. So let's see if we can see what's happening. We have the sum n equals 0 to infinity. Now we already have n factorial in the denominator, and the x plus 3 part is pretty straightforward. Notice that is just x plus 3 to the n. The tricky part is figuring out how to represent the nth derivative at negative 3. So looking for a pattern in these derivatives evaluated at the a value of negative 3. Focus on the numerator of those fractions for now. Or actually, before we do that, notice that they're all negative, so we can make it negative. Now let's focus on the numerator. We have 1, 1, 2, 6, and if we did another one, we would get 24. Notice those are the factorials. We have n factorial. But then we're dividing that by something. So let's look at the denominator. We have 3, 3 squared, 3 cubed, 3 to the 4th. So it looks like it's some kind of power of 3. Notice where it's starting. It's starting at 3. It didn't start at 1. So it looks like it's starting at n plus 1. So we have 3 to the n plus 1. When n is 0 here, we get 3 to the first, which is 3. If n is 1, we get 3 squared here, and so on. Notice now we can simplify this sum. We have n equals 0 to infinity, negative. The n factorials will cancel, leaving us with x plus 3 to the n divided by 3 raised to the n plus 1. Our goal now is to find the radius. So we'll need to do the ratio test. Remember the steps for that. We have the limit, n goes to infinity, of the next term divided by the current term. So limit, n's getting really big. The next term is x plus 3 to the n plus 1. I'm going to ignore the negative since it's in absolute value. It's going to go away. And then in the denominator, we have 3 to the n plus 2. And all of that is divided by the current term, x plus 3 to the n divided by 3 to the n plus 1. Let's rewrite this. We have the limit of x plus 3 to the n plus 1 divided by 3 to the n plus 2 times the reciprocal of the denominator. That is 3 to the n plus 1 divided by x plus 3 raised to the n. Let's see if we can reduce any of those. Notice we have x plus 3 to the n plus 1 and x plus 3 to the n. We can reduce the factor x plus 3 to the n, and you'll be left with x plus 3 in the numerator. Similarly, with the 3 to a power, we can reduce that, leaving us with 3 in the denominator. After all of that, we now have the limit as n approaches infinity, absolute value of x plus 3 divided by 3. Well, that's simply going to give us absolute value of x plus 3 divided by 3, and we want that to be less than 1 for the ratio test. So solving this, we get x plus 3 is less than 3. And from here, we can say that our radius is 3. In this example, we again want to find the Taylor series for f centered at pi halves, and we'll find the radius of convergence. Let's start by listing out some derivatives. F is cosine x. F prime would be negative sine x. Second derivative is then negative cosine x. Third derivative, positive sine x. And then the fourth derivative is just going to cycle back to cosine, and that pattern will continue. Next, we'll plug in a. So f evaluated at pi halves. Cosine of pi halves is 0. F prime at a. Negative sine of pi halves is negative 1. Second derivative, that is negative cosine of pi halves. That takes us back to 0. Third derivative at pi halves. Sine of pi halves is 1. And then the fourth derivative is going to take us back to cosine, and we cycle back to 0. And that pattern's going to continue. So now we can write f as the sum from n equals 0 to infinity, f to the n of a, which is pi halves, times x minus pi halves raised to the n divided by n factorial. Let's list a few terms. When n is 0, we simply get 0. And then when n is 1, we'll get negative 1 divided by 1 factorial, which is just 1, times x minus pi halves to the first. Plus, again, we get a 0, plus, when n is 3, 1 divided by 3 factorial, times x minus pi halves to the third, and then a 0, and then 1, actually negative 1 divided by 5 factorial, times x minus pi halves to the fifth, and that pattern is going to continue. Next, let's rewrite the sum. But before we do that, recognize that this sum starts at n equals 0. So we have our 0th term, our first term, our second, third, fourth, fifth, and so on. But half of those are zeros. Let's focus on the terms that are not zeros. So we can think of this as our new 0th term, our new first term, our new term, and so on. And when we do this, we could, if we wanted to, use n again, but it would be a different n. It would not be the same n that we have up here. So rather than using n again, let's use k to kind of distinguish between the two. So we have k equals 0 to infinity. And now let's see if we can recognize what's happening. Notice that we have negative 1, positive 1, negative 1, and so on in the numerators. Those alternating signs are happening. So we know we've got negative 1 to the k this time. We're no longer dealing with n's. But is it k or is it k plus 1? Let's go through and test that. When k is 0, we have negative 1 to the 0. That would be a positive 1, which doesn't match up here. So let's make that k plus 1. And now the signs will match up with those negative, positive, negative, and so on. We also have x minus pi halves to a power. And recognize what those powers are. We have 1, 3, 5. The next one would be 7. Those are odd powers. And the rule that we use for odd would be 2k plus 1. Notice that the denominators, the factorials, are also odd numbers. So in the denominator, we can use 2k plus 1 factorial for the denominator. Next, we want to use the ratio test. We have limit k is going to infinity, next term, divided by the current term. That is the limit, k is getting big, of negative 1 to the k plus 2 times x minus pi halves raised to the 2k plus 3. That might be a little tricky. Think about that as 2 times, we're replacing n with k plus 1 plus 1. And then that is divided by 2k plus 3 factorial, again for the same reason, divided by the current term, negative 1 to the k plus 1 times x minus pi halves to the 2k plus 1 divided by 2k plus 1 factorial. Now writing this out again, we'll just copy the top fraction for now. And multiply by the reciprocal of the denominator, that bottom fraction. And now we'll go through and see if any of this reduces. Really, the alternating part we can ignore since this is just inside absolute value. The negative is not going to matter. So let's focus on the others. Looking at the factorials, 2k plus 1 factorial and 2k plus 3 factorial. The 2k plus 1 is going to go away, and then the 2k plus 3 will be left with 2k plus 3 times 2k plus 2. And looking at the x minus pi halves factor, we can reduce that and we'll be left with, in the numerator, x minus pi halves squared. So simplifying all of that, limit k is going to infinity of x minus pi halves squared divided by 2k plus 3 times 2k plus 2, and this limit is going to 0, which we know is less than 1 for all x, which means our radius is infinity.